right, can everybody hear me okay? Yep. Perfect. So thank you all for coming for the talk on Introduction to Natural Language Processing. Before we start, a huge thanks to Data Science Dojo for hosting and for refreshments. My name is Rutu Mulkar. A little bit about me, I am the founder at Hunchera, which is a platform to help you understand language, making it simple. I have a Ph.D. in computer science with a specialization in natural language processing. Before Hunchera, I was a founder at Ticary Solutions, which was sold to Sigmoidal early this year. I was a contributor to IBM Watson, which helped defeat humans in Jeopardy. And before that, I worked at PwC, IBM, Moz, and Precise Health. So I've worked at a varied number of NLP problems in so many different spaces. And I'm really excited about this space. So in this talk, I have consolidated NLP topics into 3 sections. First is the syntax and semantics of English language. There we'll learn about how language is structured and how we derive meaning from that structure in English. Next, we'll talk about language models, which is converting text into a series of probabilities, and how we are converting text into numbers. And finally, we'll talk about word embeddings, which is learning the semantics or the meaning of the text in the form of a mathematical vector. Before we start, if you have any questions while we are talking about the content, just feel free to stop me, feel free to ask questions. Let's make it as interactive as we can, because the goal is to help you understand all of these concepts of NLP without having to read blogs and books and all of these other things that you otherwise would have to do. So let's start with syntax and semantics of English language. What is syntax? Syntax is basically the grammatical structure of a sentence. So something as simple as, well, a sentence can be broken down into a noun phrase and a verb phrase. Noun phrase can be of type determiner, adjective, noun. Verbs can be broken down, verb phrases can be broken down into verbs and adverbs and so on. So basically what we are doing is we are creating these rules that can deconstruct a sentence into its individual components. Now if we do something like this, given a sentence, we can break it down to say sentence has the components NP and VP. NP has a component determiner, adverb, adjective, and a noun. And determiner, in our list over here, in our dictionary over here, we have the and a as a determiner. So we'll just place one of them as the determiner. Adjective, we just know one adjective, which is happy. And in this way, using these rules, we are actually creating sentences based on the knowledge that we have about what syntactic component of a language corresponds to what kind of a lexicon or a word in the language. The goal for understanding the syntax of language is to be able to understand the meaning of the language. What are they trying to convey? And that is semantics. That's what semantics means, the actual meaning that's being conveyed in the language. But it's not super easy. So syntax and semantics of text is hard. Children make delicious snacks. Are you eating, children? Or are the kids making some snacks? Yeah, this is taken from a tagger called Spacey, and here's what it has derived the links between delicious snacks and children to be. Make, the subject of make over here is the children, and the object is delicious. So it's still kind of ambiguous as to what is happening here. Are the children making the snacks, or are the children the snacks? I saw the Grand Canyon flying to New York. This is interesting because who's doing the flying here? Is it you who's doing the flying, or is it Grand Canyon who's doing the flying? Now this parser thinks the flying, the subject of the flying is Grand Canyon. So it knows nothing about the size of Grand Canyon and about the fact whether a plane can carry Grand Canyon, but based on how the sentence is defragmented or destructured, this parser seems to think that the flying is done by the Grand Canyon. So you are seeing Grand Canyon flying to New York, which is semantically incorrect. And so our parser hasn't able to capture the meaning of the sentence as it should be. Stolen painting found by the tree. Who's doing the finding here? If we change the sentence to stolen painting found besides the tree, we can see that the besides is the object of the tree, and the finding, the stolen painting is found, and then there's a preposition which means it's an expansion of this statement, stolen painting found besides the tree. Whereas up there it says stolen painting, agent is the tree, agent of the finding is the tree. So parsers don't quite know how to deconstruct a sentence or how to extract meaning from a sentence because they don't know semantics, they don't know the meaning, they don't know how things are expressed by humans. Context matters a lot. Monkeys like bananas when they wake up. Well, who wakes up? How is this sentence structured compared to monkeys like bananas when they are ripe? So in the first sentence, they is actually monkeys. In the second sentence, they actually refers to the bananas. So we were just talking about pronoun resolution and how hard it is. A pronoun is words like they and them and him and her, where we are not explicitly mentioning who that person is or who that object is. And it's assumed based on the knowledge of the world that you have. You know that monkeys usually don't get ripe, right? Bananas get ripe, but monkeys getting ripe is weird. So as humans, we can process this pretty quickly. But getting a machine to do that is hard. Here are some ways in which we can actually do that. We can get a machine to do that. These underlined words are some weird words which don't exist. But based on the context, all the Waltals were delicious. What do you think Waltals is? Is it a noun? Is it a verb? Or is it an adjective? Noun, because it sounds like a noun, it looks like a noun. How about delicious? Adjective or maybe noun. How about it was calicial? What else would you replace calicial with? It was good, it was nice, which are all adjectives. So we can infer the part of speech of a word based on the context that it exists in. And here are some examples of part of speech tags that we would usually use in a regular sentence. There are way more than this, but these are the top few ones. So the question is, well, do you want to build your own tagger? You want to build your own system that can capture these relationships? You need some kind of data. And here are two data sets which are often used. The Penn tree bank corpus, don't use it. I mean, you can use it, but you'll have to spend $1,700 in order to get access to that database. The Universal Dependencies corpus is a much newer one, and it's available for free, which you can use to train your own corpus. But there are several tools. If you don't want to train your own corpus, use an off-the-shelf system that has been trained on universal dependencies and a bunch of other data to tag, to find dependencies between words and also inter-sentence dependencies. SpaCy is fast, it's accurate, it's written in Python. Stanford Core NLP is a little bit older. It's written in Java. Last I checked, it was slower, but they've fixed it in 2018. NLTK is a good software to use if you're just starting out in NLP and you want a tutorial. I have not seen it being used in any production level software.
So, Rutu, a question. So, why would anyone go for directly to the corpus and build their own as opposed to using the library? I mean, is there a scenario that you would?
Yeah, so the question is why build your own parser and why not use it? Most people would use an off-the-shelf parser. But oftentimes there are cases where you need to either retrain an existing model or train for new entities. Like I was working on a project with BP actually, and they have these oil wells, which are very specific about how these oil wells are mentioned. They have their own, they're not nouns, they're not adjectives, they're just these strings which are pretty random in text. It might be alphanumeric. So there is no regular expression, or there is no specific way to identify it. So they're like an entity in themselves. So in cases like that, where we are in some sense introducing a new type of part of speech tagger, that's when we need to retrain it.
Let me rephrase. I'm sorry. I think I probably did not ask the question correctly. If you go back to the previous slide, so what this corpus is? So what do we have in this corpus? I get what you.
Okay, got it. So why use this corpus if that?
Not go to the library?
Yeah. So the libraries have a very good coverage in English. They might not have coverage in different languages. The universal dependency corpus has a lot of these taggings in different languages as well, which is one of the most important pieces, which is why you might want to go here. But apart from that, training a corpus from scratch, training a model, a part of speech tagger from scratch, is probably not the best use of time unless you're a researcher and you're looking to kind of get your feet wet with that.
So one of the things in this corpus is that banana's ripe. Am I getting it right?
It says that bananas are nouns, and you know, ripe is an adjective, and that's the tagging that's mentioned. And what you want to do is, based on how words are tagged, create a machine learning model that can learn that automatically. So once you get a new sentence, it should be able to get that dependency.
Can a banana be aggressive or intelligent or something?
If there is a sentence about that, that's what the system does. Yeah.
Could we attribute the machine learning errors more to malformed sentences with dangling participles rather than fault in the lack of context itself?
Yes. I mean, if there is, so if there's a dangling participle, or if it's not a well-formed sentence, I am a, and if there's a period at the end of it, and it's not really a well-formed sentence, then the probability of that sentence existing gets pretty low. But this corpus is actually a nicely trained data set that you can learn, and so it represents a good chunk of how text exists in the real world. And so anything, if you find these mistakes in the real world, it would be a much lower probability, and the system would do its best to classify whatever it has as something. In, you know, like I am a, okay, I is a noun, there's a pronoun, am a determiner, and then some things to be expected, but you don't have that yet, so that's what it'll do.
So, I'm sorry, just one last question. So how are these different from, Google also has this language model, and Google's corpus would be much bigger than potentially any other corpus that is out there, right? So how's that different? And my knowledge is limited in NLP, so I'm just asking.
Yes. No. So the question is, how is Google's language models different, or other models out there? So I'll come to language models as the next section, but the part of speech taggers that you will find, most of these are the Stanford Core NLP and Spacey are the state of the art in terms of tagging sentences with their right part of speech. What Google has done is more with probabilities and statistical NLP. So although they may use some of it, they haven't released anything that does this part, which is look at the dependency between the words, look at how they are linked, who is the subject, who is the object. What they've looked at is n-grams of words, that is probabilities of multiple words occurring together. Apples and bananas and oranges, you know, that's apples, bananas and oranges. It's a 4 word phrase, and this is the probability of that. It's a high probability. But having sunglasses and bananas and oranges is a low probability. So that things like that, which is modeling how multiple words occur together, is what they have released as a Google Ngram corpus.
Okay, and the corpora only give us the parts of speech, what part of speech a specific word is.
Yeah, so part of speech and the dependencies between them.
Okay, thanks.
So, sorry, are the taggers rule-based or are they also trained on models?
They are statistical. So Spacey is, they've actually they've trained it on PyTorch and a bunch of other newer models that were released.
So you could potentially use different models with Spacey if you had access to it?
What do you mean you can use potentially different models with Spacey?
So Spacey is using a model to extract, I guess, what word is what?
Yeah.
To tag all the words.
Yes. So there is a model that Spacey has trained, and that model can predict with some degree of accuracy that this word is a chair, is a noun, and a chair is used for sitting, and these are the part of speech tags, and this is how these words are linked. So there's one model though and that model's job is to assign a class to a given word.
That's fair, but if you had a really different sort of corpus, if that's the right word, then you could use Spacey to tag using your own model if you were to train that.
The using your own model thing is confusing to me. Because if you're using Spacey as a model to classify, if you're in the machine learning space, think about it as you are using one model for prediction, right? And then you have data and you're predicting it based on that data. So where does your model come in? Are you training a new model, in which case you take their model and you add...
The problems that you were describing, like say for the BP scenario and so on. So if you had a really different sort of corpus, then you would want to train
your own model. So in that case, you don't use the off-the-shelf ones. You train your own models for that. Perfect. Yeah. Any other questions? Yeah.
How will this tagging perform in less standard forms of English, like more colloquial sentences? Does it apply to that?
Good question. So how does this perform with more colloquial sentences? And this has been a constant catch-up game because it's great for well-formed sentences. But the English constantly changes. Things like microwave and Google have become verbs now. Inadvertently they are used as let's Google it instead of let's search for it or let's find it, or let's microwave it instead of let's heat it up. So it's always an evolution. These parsers are good with some degree of accuracy, and there's always that error rate, and there's always this catch-up game that okay, now people are using words differently, and let's catch up with that. This is especially true in things like sentiment analysis, where people have creative ways in which they would say something bad or say something good. And my favorite example, and you'll find me quoting this all the time, is something like, this movie is great for a Sunday afternoon nap. They're saying this is a terrible movie, but they said this movie is great. How the heck can a machine figure out that this is a terrible review? So it's a catch-up game because we change the way we speak.
This is slightly off the subject, but I was musing today. I was wondering if it is possible for a machine to detect sarcasm.
Yeah, there's been some work that's been done.
Is that a difficult problem?
It is, because humans can't detect sarcasm that easily. So unless humans do it really well, you cannot train a machine to detect sarcasm really well. Okay, so what can we do with part of speech tags? We can do keyword extraction because nouns and noun phrases are usually the keywords that we are looking for in a paragraph. Entity extraction. What are the names of places mentioned in a news article? So here's an example. Elon Musk has shared a photo of the spacesuit designed by SpaceX. This is the second image shared of the new design and the first to feature the spacesuit's full body look. And here you can see that the system is able to identify not all, but quite a few of these keywords that are relevant in this paragraph. And most of them, in fact, all of them are nouns. So how are these extracted? Well, a generic way to extract keywords is extract all the nouns and then filter these based on what is the most likely match with what you're looking for. And that's usually something that's very specific to a company. So for instance, if you're doing search engine optimization, your keyword search is very specific to that. How do you rank high in Google? That's what SEO is. If you're in the medical field, you are optimizing over something else. You want to know, does this patient have pneumonia or not? And how are the different ways in which this pneumonia concept can be mentioned? So based on the space you're in, you might extract all the nouns, but then to filter it, you want to figure out how are you going to do that. I talked briefly about SEO, and one could potentially use part of speech taggers for keywords and for extracting keywords. Customer feedback analysis. You're given some information about how the customer interacted with your product, and you want to understand very quickly what they liked and what they did not like. How do you do that? Using extracting keywords for it, figuring out what they liked, what is an important keyword, like smaller fees is a keyword. Are they associating it with a positive sentiment or a negative sentiment? And that way we can aggregate all of the customer feedback very quickly. So that brings me to the end of the first section, which is the syntax and semantics of English language. The next section is about language models, and that goes to Raja's question about the difference between Google's language models and others that are available. So,
just before you jump up,
yeah.
Are there tools for the keyword analysis and sentiment analysis as well? Like you mentioned, Spacey do that, or are there other tools that do that?
There are several. I haven't listed them out here though. No, why don't we connect after, and I can point you to some. So what are language models? So when we used grammar, we broke down the whole concept of a sentence into its part of speech tags. Now, if we have very few of these rules in our system, we would get just one or two representations of how these words occur in text. Using language models, we are basically moving away from that and getting probabilities of how words co-occur in text. So something like, if you have a model can predict the probability of a given word and a list of based on a list of previous words. So if you have the phrase natural language processing, what's the probability of all of these three words occurring together? It's the probability of the word natural times the probability of the word language given you already have natural times the probability of the word processing given that you already have natural and language. So you are basically taking these joint probabilities to see what's the probability of natural language processing versus natural language chair. And you would see that based on how words actually occur in text, you don't see instances of natural language chair. You do see instances of natural language processing. And based on that, you can model English in a much better way.
Just a quick question. So is the probability the same as the probability of processing and then given processing and the language? So you reverse that. So you first here choose natural and then language, natural and then processing. So I'm just wondering if you first choose processing and then second choose.
Well, so we are reading English from left to right, right? So in English, when we see just the word language, natural language, we want to see what's the probability of language given the word natural.
So you always start from left to right.
Yeah. If it's Arabic, then we would start from right to left.
Well, you could go the other way, but you'd have to say the probability of processing times the probability of processing preceded by language multiplied by the probability of processing preceding language preceding natural,
which is kind of unintuitive when you think about it. Like yeah. Two questions. I saw you first. I'll come to you.
Well, I was thinking, like, in this example, you know, well, I don't know, maybe I'm wrong, but maybe you know what the word is, but like, what if you say the sound quality wasn't so good for natural, so you might want to prefer to run it in reverse?
The sound quality wasn't too good for natural. So what happens is that the sound quality wasn't too good, and it'll take in whatever word that it got. You're listening to this left to right. You're listening to the word natural something, which is garbled. Maybe you heard natal, N-A-T-A-L instead, natal language processing. And the system comes up with that, and it says, wait a second, I haven't seen any 3 grams, which means 3 words, like this before. I have seen natural language processing, which is the probability of that is by far higher than natal language processing. So that's what it does in real time. If you pull out your phone and if you...
I mean, I wondered if the confidence of the first word is low, if you could do a more efficient search by starting from the words that it's pretty sure about.
So if the confidence of the first word is low, the confidence of this entire phrase goes down, right? So the system knows that this phrase that it has isn't something that can really exist in text. So it'll look for other phrases which with the same language and processing to say what else can be highly probable in text. So looking at the first word is kind of pretty important, right? Your question?
Yeah, does this have any usages beyond speech recognition?
I'm going to come to that. Several, yeah. So, but can you see a problem with using something like this? Like in a large sentence, right? It could kind of go on and on and on. Like you have this, natural language processing is a very interesting field. And so you have the probability of all of them occurring together is the probability of the first and second given the first, third given the first and second, and it can keep going on and on all the way till the last word, where field, the probability of the word field given this whole sentence. And so computation of that gets pretty intensive. And we need to figure out a way in which we can reduce that big chain of probabilities. Does that kind of make sense? Okay, good. So luckily, we have something. So we can use Markov assumption, where he said, Andrei Markov, he said that one can make predictions for the future of a process based solely on the present state, just as well as one could, knowing the process's full history, hence independently from the history, which means probability of pleasant given the weather is almost the same as probability of present given just the word weather. So we have this simplifying assumption where we are rounding things up and we are saying, let's just look at a certain number of n grams, which means we have this window where we say we look at 2 words together or 3 words together or 5 words together, but definitely not 50 words together, because that's kind of an overkill and it's really, really hard to process all of that information together. Any questions on that? Yeah.
I think you have to figure out which words to use or how to rank them.
Not which words, but how many words. What's the window of words? So if you're looking...
Just the window is good enough to
Yeah. Yes, I'll come to you. Go ahead.
So I want to kind of pull back a little bit here. The problem that we're facing now is that we've got a sentence of words that have been, utterances that have been picked up by a voice recognizer that is uncertain about which words are in that sequence?
No. So we are trying to model the way words exist in the world. And we are trying to figure out which words occur together and which words don't occur together, and what's the probability that these 3 words occur together.
Okay. And I'm sorry, but the purpose of that is? I'm
getting that.
Okay. All right. So it's not
calculate probability of pleasant given weather.
I'm sorry? I'll get to that. Next slide. One more question.
So I guess you can apply this recursively, but you lose accuracy with each additional iteration. Is that right? Because you could do it for a whole sentence, and then basically you're telling me that one word is useful for predicting what a word 5 words away from that is, and which is clearly not the case.
Not really. So I'm saying that all you need is a word before that, or 2 or 3 words before that, rather than all the 50 words before that.
And that kind of loses context, because the immediate word might not, I mean, sounds unintuitive that just the word before that in a very long sentence can predict with high accuracy whether the entire sentence is...
My name is. What is the next thing that you would say? Would you say bright? Would you say heavy? Would you say, you know, I'm listing out adjectives. I should list out verbs. I should list out the, things like that. You know my name is, the next word would be a noun, a name, right? So based, what this Markov assumption said is that you would want all of these previous words, right? The whole sentence in order to predict what the next word is. Ideally, that makes sense, but it's extremely hard to compute. And so when they forgot, they said, let's chop that out. Let's just assume like a small window of 5 words or 3 words and see what the probability is. They found that it was almost similar. And that's why this assumption came about, that, well, we don't need to compute all of that. Let's just simplify it, because the probability is almost similar.
So does that mean that in voice recognition, most of the time they're just going 1 or 2 words back to predict what the next one is when there is ambiguity?
I don't think so, because then I'll get to voice recognition in a bit, but I don't cover this topic. The thing is this: when you have this entire sentence, right, in voice recognition, it may use 1 or 2 words to help predict what that most likely word is. But once you have that, if you look at your dictation, it often changes the first or second word, because it may not make sense syntactically. So there are a bunch of other checks that are also in place in order to make sure whether the sentence is well formed or not. And in that case, it's looking at probabilities of that entire sentence and phrases within the sentence. So but the original assumption of this probability in the Markov assumption still holds.
So do you think as like technology evolves and like the limits of our processing power no longer becomes a factor, it will eventually drop the whole Markov assumption and just always process the entire sentence?
Not really. So here's the thing: if the probabilities are so similar, you don't really need to compute the tail end of the probabilities. As processing evolves, the models are definitely getting way more complicated, and there's a lot more that I'm not even going to start covering in this talk. But the very concept about, you can compute all of these long tail probabilities, but if you're getting a very similar number without computing all the long tail probabilities, even if you have the computation power, would you do that? The answer is going to be very similar. You can do it if you have GPUs and everything, but would you do that?
I guess like, to see like to constantly do that, like in the case of like there is just like an anomaly, like to potentially like catch those, even though those are like very, very rare.
Yeah, so for rare cases, right, it makes sense for rare cases, maybe you don't have that similarity. But in that case, there could be other checks in place, which is what we just talked about, that the sentence is not well formed. It predicted things, but sentence is not well formed, so you can use a part of speech tagger on top of that. You know, there are a bunch of other ways to do it. Any other question? Yes?
So is a 3 gram kind of a general rule of thumb for how long of a gram that works for the common English language?
Yeah, 3 grams seems to be like, you know, there are often names and concepts which Stanford Research Institute. 3 words. And it's unlikely for phrases to go longer than 3, or names to go longer than 3, although I've seen 5 and 6 grams. So it kind of depends on what text you're dealing with, and if there are these globs of text where 3 or 4 words together mean something else.
Okay. Thank you.
Sure. Any other questions? Okay. So how do we compute these probabilities? It was just a question a little while ago. It's pretty simple. Probability of a given word given the previous word is a count of those 2 words together divided by the count of the previous word. So it is similar to the chain rule that we have. And we can do that not only for the bigram model, which is 2 words together, but we can do the same thing for trigram and 4 grams and however number of grams that you want, using the chain rule of probability. And if you're not familiar with that, see me after. I'm happy to explain that to you.
So quick question is, so like 4 gram, 5 gram is the bigger number of grams always more accurate than the less number of grams?
Depends on the context of what you're dealing with. Sometimes it could add noise, because if you are looking at, say, a 3 gram, oftentimes your system will pick up this 3 grams things like it is lots of determiners, lots of prepositions. It ends up being way more noisy than what you intended it to be. So you have to be careful about what is the context and what's the data you're dealing with.
This counting is done on, I mean, how do you calculate count of WI?
So you have a corpus, you have a data set, you go through the data set in one go and you find all the unique words, or all the unique 2 words together, and you compute the count. So it's like a dictionary that you're creating beforehand, and then once you're ready to process it, you count the probabilities based on this dictionary that you have.
What's the typical size of this dictionary, especially for like that numerator?
Yeah, so most people who use language models now, they use something off the shelf like the Google Books project, where they have 2 words together or 3 words, multi-words together. But the size of it, there are lots of interesting ways to do it. You can log it, you can have the log probabilities and things. So it's again dependent on the corpus. If you're using a tiny corpus, you can get away with actually computing the numbers. Yes?
If we were to remove stop words, would that improve the efficacy of a trigram model?
I don't know. So if we remove stop words, we might remove words like the. And so, if you're using 4 grams, you might lose out on the Stanford Research Institute. But at the same time, you might lose out on, you might throw away the noise. So it depends on the context of what exactly you're looking to fix and solve.
How similar is this to how the human mind processes this? Do you also think in terms of probabilities?
So you're asking whether we as people think of word models and how words occur with each other as probabilities?
So say specifically with probabilities, which we know is a great predictor for what a certain word might be or meant to be. My question is, how does the brain process that? Are we taking the same sort of approach?
Probably, right? Like, we often think, oh, this person probably didn't mean that, they meant this, based on, can you take the clothes out of the oven? Like, well, probably meant washing machine. Like, you won't take the clothes out of the oven. No, what are clothes doing in the oven? That's crazy. So, yeah, I would say yes, but I don't know. I don't study the brain. my guess would be yes. What do you think? Maybe?
I was really coming to this from the direction of, did we try to emulate the way that humans think and program it in the same way? But it doesn't sound like that's necessarily how we got there.
I don't think so. I don't know. The human analogy of this would be deep learning. That's how neurons work. Neurons are fired in some way that we don't know how it is. And so deep learning is kind of the analogy of how the brain works, where each neuron has an activation function, and if it's activated or it's not activated, and that's how there's this deep learning thing, and you suddenly have an answer that works really well. Okay, so how do we use language models? Is it? Yeah, okay, spell check. If you wrote a sentence, the weather is pleasant versus the weather is pleasant, the probability of the second one is pretty low because there's no word like pleasant. There's a word pleasant, so it'll try to. P-L-E-A-S. So, but even that misspelling is probably higher in probability as compared to the one. Thank you for catching that. Speech recognition. So I have the same example. Yeah, but the weather, if you look at the spelling of weather, which weather is it? It's pronounced the same way, you know. Is it the weather or is it the questioning weather? And so based on these probabilities, even if the speech recognition system picked the wrong one, once you have this entire probability, you'll see that this is lower, it's probably the other one, and the system would switch it out.
How do you come up with candidates of what to compare with?
Candidates of what to compare with, that
for
is...
the spelling one, I mean for the speech maybe just trying to find similar sounding words, but
yes.
For spell check you would have like... Similar
text words. So there are different ways in which words are similar to the other. Like sounding, it has to be, you know, they need to be homonyms. But in text, there is this thing called Euclidean distance, where you're looking at these words. How many characters of this word do you need to change in order to get to that word? And the closest ones would be the highest candidates, most likely candidates. Machine translation. High winds tonight versus large winds tonight. They meet. The second one sounds weird, even though high and large are kind of similar in meaning. So you would pick the one that has higher probability when you're translating from one language to another. Predictive text. I have forwarded my email or resume. You can see that on your phone. You know, it's there. We use it on a daily basis. Language models to check out. The Google Ngrams, they've looked at a lot of books and come up with these Ngrams which are free to use and free to download and work with. Okay, so we talked about syntax and semantics. We talked about language models. And the final aspect of the talk is about word embeddings. Any questions so far about language models? Okay. I'll have the slides up after the talk, probably tomorrow morning. So if you are looking for any of the links, feel free to grab them. Okay, so what are word embeddings? Has anybody worked with word embeddings? Cool, one person, yay. So word embeddings are vector representations of word in order to capture the actual meaning of that word. Now, what that means is, if you have the word the, and you have a list of numbers to capture the meaning of the, that's basically a vector that represents the word the. In this case, it's totally arbitrary. But here's an example of, we call it one-hot vectors, which means that it's a binary vector. In this case, there are two sentences. Have a good day, have a great day. The total vocabulary is 5 words. That's have, a, good, great, and day. And what we've done is in this vector, oh, you can't see my mouse. In this vector, have takes the first position in the vector. A takes the second position, good takes the third position, and so on. So each of these words is given a position in the vector, which is 0 or 1, based on whether that word exists in the sentence or not. So if you're taking if you're representing have a good day in a vector form, we would have everything as 1 in the vector except the word great, which is 0, because the word great doesn't exist in that sentence. So this is just one example of creating a vector from a sentence. But there are so many different ways, and what word embeddings has done is that it has captured the vectors of a word in a way that we can actually do mathematical computations on words. So there are two examples of word embeddings that are very popular: glove and word2vec. In the previous example, I showed vectors represented in 5-dimensional space, right? There are 5 dimensions of the vector. So if you are trying to project it on a paper, there'll be 5 dimensions. These models can go over 300 dimensions. There are 300 different fields in there for representing each word. And there are 2 ways in which word2vec works. One is they're both not a deep learning, but it's a neural network. And one of them is a skipgram, and the second one is a bag of words model, or CBOW. What CBOW does is that it takes the context of words and it tries to predict the center word. So there's a sliding window. You're given each word. You're given the context, and you're trying to predict this word. And it keeps going in order to predict what this word is, given the context. Yeah?
So the or the BOW means a bag of words.
Yeah. Common bag of words, I believe. Yeah. Skipgram, it takes a word and it tries to predict the context of the word based on this given word. And I'm not going to get into the math of it and how that works. But using that, basically one can figure out how to represent any word in the vector space. To give an example, I wanted to add it to the slides, but I didn't, but I will mention it. We can do mathematical computations on concepts like king minus man plus woman equals, and the system will tell you queen. So it has understood these concepts in some mathematical way about what king is. You're subtracting man, you're adding queen. It keeps that royalty concept and it presents queen to you. It can understand relationships between countries and capitals. It can understand similes, like, if you give it names of 2 mountain ranges, it'll tell you the 3rd mountain range. So it's pretty interesting about how they came up with something like this. And you can go and download word2vec or use an online source to play with word2vec. But it's this model was released in 2013 on data that's not released, but Google did release the model, and a lot of people have done a lot of interesting things with this. It kind of changed the way we perceive NLP because of now we can understand semantics with numbers. So we can process meaning with vectors, which is pretty insightful. So what can we do with word embeddings? Well, we can identify topics. We can use it as a thesaurus. And now we are using it as input to these highly complicated models like BERT, which came out in last year, 2018. Another deep learning model by Google, which has been beating all of these tasks that we have in different spaces, like question answering or most of the generic NLP tasks. So we are kind of at that point where a system that's not trained on a specific data can still do reasonably well as a system is doing that's just trained on that data. So we're getting to the point where we can do transfer learning. I learned something from news, but I can answer something from blogs, which is pretty interesting and insightful. So that brings me to the end of this topic. And so to summarize, we talked about 3 things: syntax and semantics of English. We looked at part of speech tags. We looked at dependencies between words. We talked about language models and probabilities and how words co-occur with each other. And finally, we talked a little bit about word embeddings and how words are represented and sentences are represented as vectors. And that's it for now. Thank you so much. Any questions? Any additional questions?
So you just mentioned a bird, so it's B-E-R-T?
B-E-R-T, BERT, yeah.
So it's more accurate and better to use than the word to vector?
So they're different things. BERT is it's a deep learning model, whereas word to vec or glove is a word embeddings model. So they're two very different things. There's actually a talk on BERT coming up in January, mid-January. So if you guys are interested in BERT and ExcelNet and all of these more complicated machine learning models, NLP models, feel free to come to that one.
And there's another book called Doc to Vec.
Doc to vec, that's based on word to vec.
Okay, so
It's similar, very similar, yes. But it's from capturing document as vectors as opposed to words as vectors. If you have any questions and if you don't want to ask, you're welcome to come to me right now, or you can email me also, or tweet to me, but that will be public again. So email might be better if it's just a one-on-one thing. Hey, thank you.